December 11th, 1943. Wright Field, Dayton, Ohio. The morning air carried the metallic scent of aviation fuel and winter frost across the experimental airstrip, where a single P-51B Mustang sat motionless under gray skies, its aluminum skin reflecting pale sunlight like polished silver. Test pilot Robert Chilton stood beside the aircraft, clipboard in hand, reviewing performance specifications that promised nothing extraordinary. A capable fighter, certainly, but not revolutionary. North American aviation had delivered a competent design, a long-range escort fighter that would protect bomber formations over Europe. The Army Air Forces expected reliability, not miracles. Chilton had flown 43 combat missions over North Africa and Sicily. He understood machinery, limits, physics. He knew what aircraft could and could not do. What he did not know, what nobody yet comprehended, was that this particular Mustang carried a modification so subtle, so seemingly insignificant, that it had been logged as a maintenance error in the pre-flight documentation. A radiator scoop, positioned 6 inches farther aft than standard specifications dictated. A misplaced component. An engineer's miscalculation, or so it appeared. Chilton climbed into the cockpit, secured his harness, and prepared for what he assumed would be another routine evaluation flight. He was wrong. Profoundly, historically wrong. The North American aviation engineering team had been wrestling with a fundamental contradiction since 1940. The P-51 possessed an elegant airframe, low-drag laminar flow wings designed by Edgar Schmood, a fuselage that sliced through air with minimal resistance, and the British Rolls-Royce Merlin engine that transformed the aircraft from adequate to formidable. Yet even with these advantages, the Mustang suffered from a persistent aerodynamic penalty that plagued all liquid-cooled fighters. The cooling system itself created drag. Every radiator, every scoop, every intake necessary to prevent engine overheating acted as an airborne anchor, bleeding speed and efficiency. Engineers understood the mathematics. Cooling required airflow. Airflow meant openings in the fuselage. Openings meant drag. The equation seemed immutable, an unavoidable compromise written into the physics of high-performance aviation. The German Messerschmitt Bf 109 accepted this penalty with its underwing radiators. The British Supermarine Spitfire embraced it with cooling scoops that created measurable resistance. Every nation-building liquid-cooled fighters faced the same fundamental problem: how to cool an engine generating 1,500 horsepower without sacrificing the speed that kept pilots alive in combat. North America's solution had been methodical, conservative. Place the radiator scoop beneath the fuselage, behind the wing's trailing edge, where it would draw cooling air without catastrophically disrupting airflow. Design the intake to be as small as aerodynamically feasible. Accept the drag penalty as inevitable. The resulting configuration worked adequately. The P-51 could fly, could fight, could escort bombers deep into occupied Europe. It simply wasn't exceptional. But in the experimental shop at the Inglewood, California plant, engineer Beverly Howard had been conducting unauthorized calculations. Howard possessed a reputation for unorthodox thinking, for questioning assumptions that others accepted as gospel. He had studied the work of NACA, the National Advisory Committee for Aeronautics, particularly their research into the Meredith effect, a theoretical phenomenon suggesting that under specific conditions, a properly designed radiator installation might not merely minimize drag but actually generate forward thrust. The concept seemed to violate intuition, that the very system designed to cool the engine could simultaneously propel the aircraft forward. Howard believed it was possible. His colleagues believed he was wasting time. His supervisor believed he was insubordinate. None of them yet understood that Howard had stumbled upon one of the most significant aerodynamic discoveries of the war. The Meredith effect, named for British engineer Frederick William Meredith, who first articulated its principles in 1935, rested on an elegant thermodynamic observation. Air passing through a radiator doesn't merely cool the engine, it gains thermal energy. This heated air expands, increases in velocity, and if channeled through a properly designed duct with a divergent exit, can be expelled at higher speed than it entered. The momentum change creates thrust, not hypothetical thrust, not negligible thrust, but measurable, significant forward propulsion that could potentially offset, or even exceed, the drag created by the cooling system itself. The challenge lay in execution. The effect required precise geometry: intake area, duct shaping, radiator core positioning, exit dimensions, all calibrated to exact specifications. Too large an intake and drag overwhelmed any thrust benefit. Too small and cooling became inadequate. Too steep an exit angle in the expelled air created turbulence rather than clean propulsion. The margins were narrow, the calculations complex, and the consequences of error potentially catastrophic. An overheated engine meant forced landing, capture, death. Howard's unauthorized experiments had suggested a radical repositioning of the radiator scoop, moving it 6 inches rearward and slightly lowering its position relative to the fuselage centerline. His calculations indicated this placement would optimize the duct length, allowing heated air to expand more completely before exit, maximizing the Meredith effect while maintaining adequate cooling capacity. He had drafted technical drawings, prepared performance projections, and submitted formal recommendations to the engineering review board. They rejected his proposal. Too risky, too theoretical, too much deviation from proven design. North American aviation was producing Mustangs at extraordinary rates, hundreds per month flowing from the Inglewood assembly lines to airfields across England. The Army Air Forces demanded quantity, reliability, predictability. This was no time for experimental aerodynamics that might compromise production schedules or, worse, result in combat losses due to cooling failures. Howard accepted the rejection professionally. He returned to his assigned duties, calculating stress loads and verifying production tolerances. But he also quietly instructed machinist Eddie Larson to fabricate a modified radiator scoop assembly according to his redesigned specifications. Not for installation, Howard emphasized, merely for bench testing for future reference for intellectual completeness. Larson complied, creating the component with characteristic precision, then stored it in the experimental parts inventory, labeled and cataloged according to standard procedures. There it sat, waiting, while the war ground forward and thousands of Mustangs flew with conventional cooling systems. October 1943. The confusion began with a parts requisition error at the Inglewood facility. A production P-51B destined for the 8th Air Force required radiator scoop replacement after a minor taxiing incident damaged the original component. The maintenance log specified standard configuration, part number SC-1043A. But in the crowded parts warehouse amid thousands of components supporting 3-shift production schedules, inventory clerk Thomas McCarthy pulled the wrong assembly from the experimental section. The modified scoop, Howard's unauthorized design, bore similar labeling, nearly identical dimensions, and no obvious visual distinction from standard equipment. McCarthy installed it without hesitation, unaware he was mounting a component that existed outside official engineering specifications. The aircraft passed inspection. Quality control reviewers, examining dozens of Mustangs daily, noticed nothing anomalous about a radiator scoop that sat 6 inches farther aft than intended. The difference was too subtle, too easily attributed to normal manufacturing variation. The Mustang was marked combat ready, assigned identification number 43-452, and added to a shipping manifest bound for Wright Field, where it would undergo routine performance validation before transfer to operational squadrons in England. Beverly Howard, meanwhile, remained unaware his theoretical design had accidentally entered the production stream. He was occupied with entirely different problems, calculating wing stress tolerances for dive bombing modifications, reviewing propeller efficiency reports, attending endless meetings about production quotas. The experimental radiator scoop had been an intellectual exercise, nothing more, filed away in his memory alongside dozens of other proposals that would never see practical implementation. He had moved on. The aircraft arrived at Wright Field in late November. Ground crews performed standard pre-flight preparations, fuel system checks, control surface inspections, engine runs. Everything appeared normal. The Mustang exhibited no unusual characteristics on the ground, no obvious deviations from expected behavior. It sat on the flight line awaiting its turn for evaluation testing. Just another P-51B among many, distinguished only by its serial number and maintenance logs. Robert Chilton received the assignment on December 10th. The test protocol was standard: climb performance assessment, maximum speed runs at various altitudes, handling characteristics evaluation, range calculations. Routine work for an experienced test pilot. Chilton reviewed the aircraft's documentation that evening, noting nothing remarkable in its specifications or assembly history. He anticipated an uneventful flight, collecting data that would confirm the Mustang met Army Air Force's requirements for escort fighter service. He scheduled the evaluation for the following morning, weather permitting, and returned to his quarters to sleep. The Merlin engine ignited with its characteristic roar, 12 cylinders generating 1,500 horsepower that translated into propeller thrust and vibration through the airframe. Chilton advanced the throttle, released brakes, and felt the Mustang accelerate down right field's runway with familiar urgency. Rotation speed, liftoff, gear retraction, climb profile, all proceeded exactly as expected for the first 12 minutes. He climbed to 15,000 feet, leveled off, and began the standard speed evaluation sequence. Maximum continuous power, throttle forward, mixture rich, propeller pitch optimized. The Mustang accelerated. Chilton watched the airspeed indicator climb. 300 miles per hour, 320, 340. Normal performance for a P-51B at this altitude and power setting. He noted the readings on his kneeboard, preparing to continue the test profile at higher altitude. Then something changed. Subtle at first. A slight reduction in vibration, a smoothness to the acceleration that seemed inconsistent with standard Mustang behavior. The airspeed indicator continued climbing. 360, 375, 385. Chilton rechecked his instruments, suspecting measurement error. The airspeed indicator could be miscalibrated, providing false readings that suggested impossible performance. But the engine instruments told a consistent story. Manifold pressure, RPM, fuel flow, all normal. No excessive power demands, no indication the Merlin was being driven beyond rated limits. 390 miles per hour, 395, 400. Chilton leveled off and reduced power slightly, his mind racing through technical possibilities. Instrument malfunction remained the most likely explanation, but the aircraft's behavior, the way it sliced through air with unusual efficiency, the lack of vibration that typically accompanied high-speed flight, suggested something genuinely different about this particular Mustang. He climbed to 20,000 feet and repeated the speed run, 412 miles per hour at military power, 23 miles per hour faster than any P-51B he had ever flown, faster than the performance envelope predicted, faster than North American aviation specifications promised, faster than physics, as he understood them, should permit. He checked fuel consumption. Normal. Checked engine temperatures. Normal. The cooling system was functioning perfectly despite the increased speed, despite air flowing through the radiator system at unprecedented velocity. No overheating, no degradation in performance, no indication of mechanical stress. The aircraft flew as if it had been redesigned by invisible hands, optimized beyond the capabilities of its supposed engineering specifications. Chilton pointed the nose toward right field and descended, uncertain whether to report a mechanical anomaly or an aerodynamic revolution. The engineering investigation began immediately upon landing. Chilton's flight report triggered a response that cascaded through right field's technical hierarchy. Performance analysts, aerodynamicists, propulsion specialists, all converging on aircraft 43-12452 with instruments, calculations, and profound skepticism. Test pilots were known to occasionally exaggerate performance to interpret ambiguous data optimistically, to let enthusiasm override precision. But Chilton possessed a reputation for exactness, for conservative reporting, for professional restraint. If he claimed this Mustang flew faster than it should, the claim warranted serious investigation. The inspection team examined every component. Engine teardown revealed nothing anomalous. Standard Merlin V1650-3, within tolerance for all specifications. Propeller blades showed normal wear patterns. Wing surfaces exhibited no unexpected modifications. Control systems functioned exactly as designed. For 6 hours, engineers scrutinized the aircraft, searching for the source of the inexplicable performance gain. It was Captain James T. Murphy, a right-field aerodynamicist with a master's degree from MIT, who noticed the radiator scoop placement. He was examining the ventral fuselage with a measuring tape, validating that all components matched technical drawings when he paused. The scoop sat 6 inches farther aft than standard configuration. Murphy retrieved the aircraft's assembly documentation, searching for authorization for the modification. None existed. He cross-referenced the part number against North American Aviation's official specifications. No match. Murphy summoned the investigation team. Within 30 minutes, they had photographed the installation, measured every dimension, and documented the discrepancy. The radiator scoop was non-standard, either a manufacturing error or an unauthorized modification, but it functioned. Somehow, impossibly, it functioned better than the original design. Phone calls to Inglewood followed, urgent conversations between Wright Field engineers and North American Aviation's technical staff. Had the company implemented a design change without proper documentation? Had new specifications been issued and failed to reach evaluation teams? The Inglewood engineers were baffled. They knew of no such modification, no authorization for radiator scoop repositioning, no explanation for how a non-standard component had entered the production stream. Beverly Howard, sitting at his desk reviewing stress calculations, received a phone call from the chief engineer's office. They needed him to come immediately. Something about a radiator scoop, about performance testing at Wright Field, about a design that matched calculations he had submitted months earlier. Howard felt his pulse accelerate. He had filed those plans away as rejected proposals, intellectual exercises with no practical future. He walked to the chief engineer's office, uncertain whether he was about to be reprimanded or vindicated. The conference room at North American Aviation's Inglewood facility held 12 people, senior engineers, production managers, Army Air Force's liaison officers, and Beverly Howard, who sat alone at the far end of the polished table feeling simultaneously vindicated and vulnerable. The Wright Field data lay before them, flight test results that documented a 23-mile-per-hour speed increase with no corresponding increase in engine power, no degradation in cooling efficiency, no compromise in any performance parameter. The modified radiator scoop had done exactly what Howard's calculations predicted. It had transformed a drag-producing necessity into a thrust-generating advantage. But the validation came entangled with uncomfortable questions. Why had Howard designed components without authorization? Why had those components entered the parts inventory? How had an experimental modification reached a production aircraft destined for combat evaluation? The answers revealed a web of informal practices, inadequate inventory controls, and communication failures that made production managers deeply uneasy. In wartime manufacturing, where thousands of aircraft flowed through assembly lines under intense schedule pressure, even small deviations from procedure could cascade into catastrophic consequences. The chief engineer, Edward Horkey, posed the central question: if we implement this modification across the fleet, what risks do we accept? The room fell silent. Engineering advancement always carried risk. The risk that calculations contained errors, that bench tests failed to capture real-world complexity, that a design optimized for one condition would fail catastrophically under another. Howard had conducted theoretical analysis, but one successful flight test did not constitute proof. The Mustang might perform brilliantly at 15,000 feet and overheat fatally at sea level. It might excel in temperate conditions and fail in Arctic cold or desert heat. It might function perfectly for 100 hours, and then develop metal fatigue that caused structural failure. Yet the potential gains were extraordinary. 23 miles per hour represented the difference between catching German fighters and watching them escape, between surviving combat and dying in aerial combat, between mission success and failure. If the modification could be validated, if it proved reliable across all operational conditions, it would transform the P-51 from a capable escort fighter into the fastest operational fighter in any Air Force worldwide. American, British, German, Soviet, none possessed anything comparable. The Army Air Force's liaison officer, Colonel William Thompson, spoke carefully. How long to verify this design? Howard consulted his notes. Comprehensive testing, multiple aircraft, various altitudes, temperature extremes, extended flight duration, would require 8 weeks minimum. Thompson shook his head. You have 3 weeks. We need Mustangs over Berlin by February. If this modification works, we implement it immediately. If it fails, we never speak of it again. The validation program proceeded with compressed intensity that would have been impossible in peacetime. North American Aviation diverted resources from standard production, creating a dedicated testing cell that operated 16 hours daily. 6 P-51Bs received the modified radiator scoop installation, each aircraft subjected to punishing evaluation sequences designed to expose any weakness in the design. Test pilots flew them to altitude ceilings, dove them to maximum speed, ran them at full power until fuel exhaustion, subjected them to temperature extremes in environmental chambers, and monitored every instrument, every temperature reading, every vibration signature for anomalies. Beverly Howard barely slept. Each morning brought new data, new questions, new problems requiring immediate solutions. The modified scoop performed brilliantly at high altitude but showed marginal overheating during prolonged low-altitude high-power operations. Howard redesigned the exit duct geometry, adding a variable flap that automatically adjusted based on cooling demand. The fix worked. Another problem emerged. Turbulent airflow at specific angles of attack created drag that partially negated the thrust advantage. Howard collaborated with NACA engineers to refine the intake lip contour, smoothing airflow attachment. Performance improved further. By January 15, 1944, the testing program had accumulated data that satisfied even the most skeptical engineers. The modified radiator scoop increased maximum speed by an average of 21 miles per hour across all altitudes. It reduced cooling drag by 38%. It generated measurable forward thrust, approximately 200 pounds at high-speed cruise conditions. The Meredith effect, previously a theoretical curiosity mentioned in academic papers, had been transformed into operational reality. The Army Air Forces authorized immediate fleet-wide implementation. North American Aviation retooled production lines, training assembly workers in the new installation procedures, updating quality control protocols, revising technical documentation. The modification added approximately 4 hours to each aircraft's assembly time, a trivial penalty for the performance gain it delivered. By February, every new P-51B rolling off the Inglewood production line incorporated Howard's design. Retrofit kits shipped to England, where maintenance crews worked through cold winter nights installing modified scoops on operational Mustangs already serving with the 8th Air Force. The pilots noticed immediately. Combat reports from March 1944 documented pursuit speeds that German fighters couldn't match, escort ranges that reached deep into occupied territory, and a psychological advantage that came from knowing their aircraft was simply faster than anything the Luftwaffe could field. The Mustang had evolved from adequate to dominant, not through revolutionary technology or massive engineering effort, but through one engineer's refusal to accept that cooling systems must always be compromises, always be penalties, always be limitations rather than opportunities. German intelligence officers in occupied France read the combat reports with growing concern. The new Mustang variant, Allied forces designated it the P-51B-10, but Luftwaffe analysts knew it simply as the fast one, was appearing in increasing numbers over German airspace. Mi-109G pilots, previously able to disengage from combat by diving away, found their escape routes closed. FW-190A pilots, accustomed to speed advantages at low altitude, discovered they could no longer outrun American escorts. The shift was subtle but devastating. For the first time in the European Air War, American long-range fighters could both reach Berlin and dominate the high-speed tactical combat that occurred there. Luftwaffe engineers obtained wreckage from a modified Mustang that crashed near Schweinfurt in March 1944. They photographed the radiator installation, measured the scoop geometry, documented the duct design, and prepared detailed technical analysis for the Reich Air Ministry. The conclusions were uncomfortable. The Americans had solved a fundamental aerodynamic problem that German engineers believed unsolvable. The Meredith effect, discussed in theoretical papers but never successfully implemented at production scale, had been transformed into a practical advantage that tilted the performance balance decisively toward Allied aircraft. The Germans possessed the technical knowledge to replicate the design. What they lacked was time, resources, and industrial capacity. By spring 1944, Allied bombing had degraded German manufacturing infrastructure, scattered engineering teams, and forced fighter production into dispersed facilities that struggled to maintain standard output, let alone implement significant design modifications. The Luftwaffe was fighting a defensive war with diminishing resources against an enemy whose industrial base grew stronger monthly. Meanwhile, North American aviation continued refining Howard's design. Engineers discovered that adjusting the exit duct angle by 3 degrees improved high-altitude thrust by an additional 6%. They found that polishing the internal duct surfaces reduced turbulence and gained another 2 miles per hour. They optimized the radiator core positioning, the coolant flow rate, the air pressure differential across the system. Each refinement was small, incremental, the result of careful empirical testing rather than dramatic innovation. Accumulated together, They pushed the P-51's performance envelope steadily upward. By June 1944, D-Day, modified Mustangs equipped every American fighter group in England. They flew top cover over the Normandy beaches, intercepted German bombers threatening the invasion fleet, and ranged deep into France hunting Luftwaffe formations. The speed advantage that began with a misplaced radiator scoop had evolved into a comprehensive technical superiority that the Germans could observe, could measure, could understand, but could not match. Beverly Howard received a letter from Robert Chilton in July 1944. The test pilot, now flying combat missions with the 357th Fighter Group based at Leiston in England, wrote with characteristic directness, "The aircraft you created saved my life on Tuesday. Bounced by 4109s near Hamburg, I was able to extend away from them in level flight, something that would have been impossible 6 months ago. Whatever they're paying you at Inglewood, it isn't enough. Every pilot in this group owes you a debt we can never repay." Howard kept the letter in his desk drawer, reading it occasionally during long engineering sessions. He had not designed the radiator modification to save lives, not consciously. He had been solving an aerodynamic problem, pursuing an intellectual challenge, trying to extract maximum performance from an existing airframe. That his work translated into survival, into combat advantage, into young pilots returning from missions they would otherwise not have survived, remained almost abstract. He worked in California, calculating thrust coefficients and duct geometries. The war happened somewhere else, in skies he could only imagine, involving men he would never meet. But the letters kept arriving. Fighter pilots were not generally prone to expressing gratitude to anonymous engineers, but something about the Mustang's transformation inspired correspondence. They wrote about chasing down FW-190s that previously could escape, about escorting bombers all the way to Berlin and back, about the psychological comfort of knowing their aircraft was faster than anything the enemy could field. The letters described a war that Howard understood only through performance data and combat reports, a war of speed, altitude, split-second decisions, and the brutal mathematics of pursuit curves. The Army Air Forces awarded Howard the Medal for Merit in a ceremony at Inglewood that he found uncomfortable and excessive. Generals spoke about innovation, about American engineering excellence, about the contributions civilian technicians made to military victory. Howard listened politely, shook hands, posed for photographs, and returned to his desk the following morning to work on propeller efficiency improvements. The medal sat in his drawer next to Chilton's letter, physical artifacts of work that felt simultaneously momentous and routine. By autumn 1944, the modified Mustang had become the standard against which all other fighters were measured. Aviation journals published detailed performance analyses. Engineering schools incorporated the radiator design into aerodynamics curricula. Foreign air forces inquired about acquiring similar technology. The misplaced part had become a textbook example of how small modifications, properly implemented, could generate disproportionate advantages. The final validation came not from engineering analysis or military assessment, but from the enemy's response. In November 1944, German fighter production shifted decisively toward jet-powered aircraft. The Messerschmitt Me-262, capable of speeds exceeding 500 miles per hour, represented a technological leap beyond anything propeller-driven aircraft could achieve. But jet engines consumed enormous quantities of fuel, required extensive maintenance, and were vulnerable during takeoff and landing. The Luftwaffe's strategic calculation was stark. Only jets could compete with modified Mustangs in high-speed combat. Conventional fighters, no matter how well designed or skillfully flown, could no longer control contested airspace against American escorts. This represented a profound admission. The Germans had pioneered many aviation technologies: pressurized cockpits, ejection seats, swept wings, rocket interceptors. Their aeronautical engineers were among the world's finest, their research institutions well-funded and productive, their industrial base sophisticated despite Allied bombing. Yet they could not replicate the simple elegance of Howard's radiator modification, could not match the performance advantage it provided, could not compete except by leaping to an entirely different propulsion technology. American intelligence analysts recognized the strategic implications. An enemy forced to abandon proven designs in favor of revolutionary but immature technology was an enemy acknowledging defeat in conventional engineering competition. The Me-262 was faster than the Mustang, yes, but also rare, difficult to produce, vulnerable in the landing pattern, and dependent on infrastructure the Germans could not protect. For every Me-262 that flew, 100 FW-190s sat grounded or relegated to secondary duties because they could no longer survive combat against modified Mustangs. Robert Chilton shot down his 10th German aircraft on December 3, 1944, a FW-190D attempting to intercept B-17s near Hanover. His combat report noted that the enemy pilot was skilled, aggressive, and tactically sound. But when the 190 attempted to disengage by diving away at full power, the Mustang followed easily, closing range until Chilton achieved firing position. Speed differential, 17 miles per hour in the Mustang's favor. Altitude lost, 8,000 feet. Duration of pursuit, 90 seconds. The German pilot ejected successfully, parachuting into frozen German countryside. Chilton circled once, verified the parachute had deployed, and returned to England. That evening he wrote another letter to Beverly Howard. "I don't know how you did it," he wrote, "but every time I fly, I'm grateful you did." The war ended in May 1945. By then, modified Mustangs had flown hundreds of thousands of combat hours, escorted thousands of bomber missions, and fundamentally altered the strategic balance in European airspace. Post-war analysis conducted by Army Air Forces historians calculated that the radiator modification contributed to approximately 400 additional bomber crews returning safely from missions they would otherwise not have survived. Roughly 4,000 men, representing incalculable human value in families not shattered, children not orphaned, futures not destroyed. Beverly Howard never met most of the pilots whose lives his engineering work affected. He received occasional letters, sporadic correspondence from men who wanted him to know his work mattered. He answered politely, deflecting praise, emphasizing that he had merely applied existing aerodynamic principles that others had discovered. The Meredith effect was not his invention. He had simply recognized its potential application and pursued implementation despite institutional resistance. Any competent engineer would have done the same, he insisted, though the evidence suggested otherwise. Dozens of competent engineers had examined the Mustang's cooling system. None had seen what Howard saw. The Medal for Merit sat in his drawer for 40 years. When asked about his war work, he would mention it briefly, then change subjects. He was uncomfortable with attention, uncomfortable with the notion that his contribution was somehow exceptional. He had been an engineer doing engineering work, solving problems using mathematics and physics. That this particular problem happened to involve life and death, victory and defeat, seemed almost coincidental. He would have pursued the same solution regardless of context, driven by intellectual curiosity rather than martial necessity. Robert Chilton survived the war, completed law school, practiced in Ohio for 35 years. He kept a photograph of the modified Mustang on his office wall, next to his framed test pilot certificate, and a letter from Beverly Howard thanking him for his first correspondence. Chilton never forgot that December morning at Wright Field, the moment the airspeed indicator climbed past 400 miles per hour, the recognition that something fundamental had changed about the aircraft beneath him. He attended an aviation history conference in 1983, where Howard was receiving a Lifetime Achievement Award from the American Institute of Aeronautics and Astronautics. They met for the first time in person, the test pilot and the engineer, both elderly now, both diminished by time but still sharp in memory. They shook hands. Neither man was particularly eloquent about emotion. They spoke about technical details, about duct geometry and thrust coefficients. They understood each other perfectly. The P-51 Mustang's transformation from capable to dominant occurred because one engineer refused to accept conventional limitations, and because institutional systems failed just enough to allow an unauthorized component to reach an aircraft that proved its value beyond doubt. This was not a story of deliberate innovation programs or well-funded research initiatives. It was a story of intellectual persistence operating in the gaps between procedure and practice, between what organizations officially permitted and what individuals could accomplish when attention was elsewhere. The misplaced radiator scoop succeeded because it addressed a problem most engineers considered solved. Cooling systems created drag. This was understood, accepted, built into every performance calculation. That this drag might be not merely minimized but transformed into thrust seemed too good to be true, a violation of intuition that suggested the concept was flawed. Beverly Howard's contribution was not discovering the Meredith effect. British engineers had articulated it years earlier. His contribution was believing it could work in practice, calculating the precise geometry required, and persisting even after institutional rejection. The accident that installed his design in a production aircraft transformed theoretical possibility into documented reality. Without that chance installation, without Thomas McCarthy pulling the wrong component from inventory, Howard's calculations would have remained filed away. Another rejected proposal among thousands. The modified scoop would never have reached Robert Chilton, would never have been flight tested, would never have generated the performance data that forced engineering leadership to reconsider their assumptions. The Mustang would have remained slightly slower, slightly less capable, slightly more vulnerable, and hundreds of bomber crews would have paid the price for engineering conservatism. War accelerates innovation not through careful deliberation, but through brutal empiricism. What works survives. What fails is discarded. Howard's design worked, demonstrably and repeatedly, and this operational success overrode all institutional concerns about procedure, authorization, and protocol. Within weeks of validation, it became standard equipment. Within months, it became the baseline against which all fighter performance was measured. The fastest path from theory to implementation was not through formal approval channels, but through accidental deployment that proved the concept beyond reasonable doubt. The Germans understood this. Their intelligence reports on the modified Mustang were technically accurate, aerodynamically sophisticated, and strategically useless. They knew how the Americans had achieved the performance gain. They could not replicate it in time to matter. Speed of innovation had become as important as the innovation itself, and in this competition, the side that could move from concept to production most rapidly held an advantage more valuable than any specific technology. Decades later, when aviation historians examined the P-51's evolution, they focused on dramatic narratives: the replacement of the Allison engine with the Rolls-Royce Merlin, the bomber escort missions to Berlin, the aerial victories that established American air superiority over Europe. The radiator scoop modification received mention in technical appendices, a footnote to larger stories about combat courage and strategic bombing. This seemed appropriate to Beverly Howard, who never sought attention for work he considered simply competent engineering practice. He had solved a problem using available tools and existing knowledge. That the solution happened to matter greatly to thousands of people did not, in his estimation, make it exceptional. But Robert Chilton understood differently. From the cockpit of a fighter aircraft being pursued by enemy planes at 400 miles per hour, the distinction between adequate and excellent was measured in seconds, in feet, in split-second opportunities to extend away from danger or close toward firing position. The 23 miles per hour that Howard's design provided was not an abstract performance metric. It was the difference between living and dying, between completing the mission and being shot down over hostile territory, between returning to base and being listed as missing in action. The pilots who flew modified Mustangs over Germany in 1944 and 1945 understood this viscerally. They felt the difference in how the aircraft responded, in how it accelerated, in the confidence they carried knowing they flew the fastest fighter in European skies. Many of them never learned Beverly Howard's name, never knew that their aircraft's performance advantage originated from a single engineer's refusal to accept that cooling systems must always be compromises. They simply flew the missions, survived the combat, and returned to lives that would not have existed without advantages they could not see. Innovation happens in unexpected ways, not always through deliberate programs with clear objectives, but sometimes through accidents, through institutional failures, through chance combinations of individual persistence and organizational gaps. Howard's radiator scoop succeeded because he believed it could work, because a parts clerk made an error, because a test pilot flew the resulting aircraft honestly, and because military necessity compressed evaluation timelines that would normally kill unconventional proposals. Engineering advancement requires technical competence, certainly, but also timing, luck, and willingness to pursue ideas that others have dismissed. The war produced countless innovations. Most are forgotten. Some are remembered because they mattered, because they changed outcomes, because they saved lives. The modified radiator scoop belongs in this category, not the most dramatic contribution to victory perhaps, but among the most elegant,